they survive, but they don't reproduce very good. But there's a good reason for that. If it's not a good time and the adults are under stress, then the little settling planulae are probably not going to do any better. So why put them out now? You're sending them into death. Because all of these reasons is juvenile corals have an undeveloped immune system. They do not have the protective microbial associated DNA, the bacteria that the adults do. There's many things that the little settling ones the size of your fingernail just can't make it like the adults can. So why should the adults reproduce? They should survive. And if you've got bad times, it really is best selections for survival. And they are good at surviving. This is the same slide you saw before. They've been put into tremendous stress, but they're doing okay. The adults can adapt, but they don't reproduce. And so now what about the fast-growing ones? Well, those are the other extreme. No wonder they go extinct, because look at the predation on them. They're very favored, and yet they don't defend themselves against predators. All the predators eat acropora. And look what the predators do. You would think that would give a little bit of selective pressure to defend yourself against predators, because all the mound ones, or most of the mound ones do, at least to some extent. And they grow fast, though. That's the same site before and after. So when they come back, they grow fast. And these are all the different kinds of things that eat coral, and most of them eat acropora. But acropora doesn't even repair itself that much. It grows fast. It's not worth taking the time to repair something that's been scraped or bashed. And they also don't defend themselves against bleaching. This is a rank. These are the ones that are strongest against bleaching, up to the ones that bleach most immediately, and the branching acropora are up there. Now this is really weird. They don't defend themselves, and they're just eaten down, but there's no selective advantage to defending, and they don't protect themselves against bleaching. They don't repair very well compared to the others. Their skeleton is porous. That makes it very good for growing fast, but it's not good for wave action. This is Transect 5 in 1998 in American Samoa, and that is really bad when a storm smashes you, because then the big tabletops that one of them gets knocked over, then it's like a cannonball for the others. It's terrible, but they're not putting much selective advantage into that. They do grow back fast. This is one in about 9 years later, the same transect. And even the larvae aren't doing very well. The pool survival of larvae for acropora lives much less than the others. And also the branching corals are much thinner tissue. Like when they make themselves for speed. They don't make a real solid, robust thing. Look at the thickness of the tissue on the branches of the branching corals here. Whoops. The lower ones are the branching corals, and they're about a half to a quarter the thickness of the tissue on the more massive corals. And even considering they're thinner, they're also thinner as being more dilute. The concentration of nitrogen and carbon in their tissues of the fast-growing branching corals is much less. In other words, the massive corals are built to survive, not reproduce when it's bad conditions. And they make it through these mass extinctions. The branching corals originate when things are getting good, and then they really take over, and they do real well. But when the time comes and things get bad again, just like Faust, they owe their soul to the devil. Okay. Now, one thing that's also interesting here is that corals can adapt to temperature quite well, it looks like. They've been through 220 some million years of ups and downs in temperature. The one thing they don't seem to be able to adapt is their crystals. Remember, when you have calcite organisms and aragonite organisms, and then when the ocean changes because of continental motion, they can't change. And all it is just the same CaCO3, but how much magnesium is in there. It seems like that's so simple compared to your complex physiology to coral, but they don't seem to. And there's lots of data, many studies show that even after thousands of years where this seepage seemed to be a low pH, the corals still can't calcify any better than those that are first subjected to it. In other words, corals cannot seem to adapt to pH, but they can adapt to temperature. Now, pH has another problem, is pH and temperature, when you're adapting to it, doesn't respond. pH is indifferent, it's just low pH and it's not interacting with you, it's just causing you problems. But bio-eroders, these are almost every phylum of animal and plant and fungus and microbe can wear away at the skeleton of the coral inside. And that's different because pH and temperature doesn't fight back, but you get coevolution when you get these microbes. So the coral evolves a defense against bioeroders. The bioeroders are going to evolve again to get around that defense. And so unlike pH and temperature, who are indifferent, the bioeroders can co-evolve. And bioeroders are becoming more, this is through the geological time, and they've just been becoming more and more diverse and more adept. And they become much better. This is when corals started about 225 million years ago. And the amount of bioerosion has been increasing. This is why I think that corals we're probably going to keep, but it's going to be hard if we lower the pH. That means that the corals can still make skeletons, but it's very much more expensive. They've got to pump a lot more ions, or protons. When the pH goes down, that means there's much fewer hydrogen atom ions or protons, and that means that they've got to pump harder and spend more of their energy to deposit skeleton. And so the corals can do it, but it's an energy drain. Whereas the bivalves, or the worms and everything else that's boring into it, they're doing just fine. So you're making it more expensive for the coral to make a coral reef, and it's getting better and easier for the borers, all these many phyla of things, to erode it. So I think the reefs are going to have a real problem. Okay, just a quick tour here. Back in the, when corals first evolved in the Triassic, here's what corals that were the fast-growing corals looked like. They're not exactly branching, but we call them branching. They're, Dick would call them facile. And so, here's the difference. Back before the Cenozoic, or the recent times where dinosaurs went extinct, the main branching corals were fascioloid or dendroid, and the branching corals pretty much originated in the period we are now. What's interesting, and this is very confusing, all I'm saying here, I didn't know I can't do a map very well. I'm not good at that. And so I just went through, and here's where the fossils of Retiophilia, that's a very fast-growing coral that ecologically must be like our Acropora now. It's very fast-growing, vertical, branching, and it's found from Alaska to northern Chile in the fossil record, Idaho, Nevada, Europe, the Alps, the Caucasus, Russia, Indonesia, Japan, all over. But it's a fast-growing coral. It went extinct. Even though the corals that survived were very small, little corals, and they didn't have a big range. There was a subgroup of that range, but they were tolerant of situation. And in fact, this is the 20 genera that survived the Triassic extinction. One of them made it a while longer, and this is called the Walking Dead thing, where they made it through the Triassic extinction, but